We saw in our last video how vectors could be added together to find relative positioning of atoms in a unit cell. While we used a simple two-dimensional crystal to show the principle, the operations are readily extended to 3 dimensions. We're going to use the same unit cell to demonstrate what happens when we multiply vectors together. Firstly, rather than working with the positional vectors RA, RB, RC and so on, we're only going to work with the relative vectors within this unit cell. There are only 2 vectors of interest. The first of these, connecting A and B, we will call M. We showed how this is calculated in the previous video as I plus 3j. The second vector, connecting A and D, we will call P, which we also found in the last video to be 3i plus j. What we will now do is explore what happens when we multiply the vectors together. What we'll do first of all is to multiply as we would with any algebraic expression. We'll put the 2 terms together and multiply out the brackets. Doing this, we come up with the following expression. Notice that we've kept the vectors in the order in which they are multiplied, and that we have not made any assumptions about what the result might be. We have a problem now, however, as we clearly have 2 different things to consider. The first is, what do we do when parallel unit vectors are multiplied together? And the second is, what do we do when perpendicular unit vectors are multiplied together? Clearly we need to treat these differently, so we need to come up with a means to multiply them together and retain information. We could say that we should ignore the information from perpendicular vectors, so that these go to 0 when we multiply them together. This would give us one particular result. However, we know that 2 perpendicular vectors can work together. Forces can combine to give a torque or twist, and so the perpendicular components have to be considered in some way. Okay, so let's make the parallel vectors multiply to 0. The problem with this, then, is that parallel vectors also work together to tell us how vectors multiply in a single direction. Obviously, both of these approaches must be considered, so we need 2 ways to multiply. Fortunately, we have 2 signs for multiplication, the times or cross sign we are familiar with, but also we have the dot sign. We use these 2 signs to tell us how to combine our vectors. When we use a dot, it tells us to disregard the contribution from the perpendicular vectors to describe how a vector scales with another one. This is called the dot or scalar product. When we use a cross, it tells us to disregard the contribution from the parallel vectors, describes how 2 vectors, for example forces, can combine to give another vector, the torque. This is called the cross product, and, because it results in another vector, it is also called the vector product. Because it is a vector product, the order in which we multiply the vectors together in the cross product, we have to be careful with the ordering of the multiplication. Okay, let's go back to what we had before. Let's focus on the dot product. We've said we will disregard the product of perpendicular vectors, so going back to our expansion of vector multiplication, we have the following expression. If the value of the dotted perpendicular vectors goes to 0, and the value of the dotted parallel vectors goes to 1, then the result of this is simply equal to 6. Mathematically, we already have a function to tell us when parallel goes to 1 and perpendicular goes to 0, the cosine function. This gives us a more formal definition of the dot product using the cosine function. It happens that m dot p is equal to the magnitude of m times the magnitude of p times the cosine of the angle between them. This makes it very clear how dotting parallel unit vectors gives a value of 1, while dotting perpendicular unit vectors gives a value of 0. The formulation of the dot product means that we can determine the angle between the vectors. We know that the dot product, m dot p, is equal to 6. Rearranging the expression for the dot product means we can have an expression for the cosine of the angle between them. We simply rearrange the equation to make cosine theta the subject. We can find the moduli of m and p by using the Pythagoras theorem, and we end up with mod m mod p is equal to the square root of 10 times the square root of 10, which is equal to 10. Cosine theta, therefore, is 6 over 10, meaning that theta is equal to 53.1 degrees. Let's look at a bit more detail at the geometry of the dot product. Firstly, let's redraw our crystal structure and label the angle theta. We said the dot product considers the cosine of this angle, so this must mean there's a right angle triangle hiding here, incorporating the vector m. So let's draw it. Remember that a cosine is adjacent over hypotenuse. This means the quantity mod m cosine theta is equal to the base of this triangle. In the dot product, this is multiplied by the modulus of the vector p. This means the dot product is simply equal to the modulus of one vector multiplied by the component of the second vector which points in the same direction. We could draw this again, but now consider it from the point of view of vector p. Drawing another triangle, but this time the quantity p cosine theta represents the amount of p pointing in the same direction as m, leading us to the same end result. A dot product is only one way to multiply vectors together, and we will explore the vector cross product in the next video, showing how this can be used together with the dot product to gain information from crystallographic data.